Okay,
It's like a bicycle.
so most of us survived, right?
Yeah, we made it.
Last one.
Yeah, Benny's.
Yeah, I've gotten a couple of emails, so that's fine.
His little Pontiac
be online for them.
G6 or whatever.
Before we dive into chapter 2, is there anything from chapter 1 anybody needs resolved yet? Any questions we have with force polygons, with resolving those simply supported beams, with force resultants? Are we good? Is everybody good on those? Good on them? Okay. So we'll move on then. Chapter 2 talks about axial forces. Okay? And we have to keep in mind that now we're talking about, rather than these forces being just generalities and out in the ether, now we're going to start looking at specific cases and how forces actually act on members. Okay, and so grab the cylinder, but we can look at.
Axial forces. Pitted, so pitted.
Okay, so sorry for those of you playing the home version of the lecture, but when we're talking about axial forces, now we're just going to reduce things to one dimension. Okay, so for those of you who have taken materials 1, you've had a chance to test cylinders, right? And I don't mean to pick on you guys who haven't taken that yet.
This is a recurring thing.
Yes, it's become quite a conversational topic point for you, but it's something that we can also see within planar members, right? We can see them in columns, we can see them in footings, we can see them in any sort of combinations that we have out in the field. Okay, so we have 2 basic types of axial forces, and we've talked about this in the past. What are 2 basic types? If we're pushing down on something, what type of force is it?
Tension.
Compression,
sorry.
right? And if we're actually pulling on the body, then we're talking about tension, okay? And this is all fine and good if we have pure compression and pure tension, okay? But what we'll find as we're discussing is that it's very rare that we can actually exert just these forces, okay, out in the field. So something to keep in mind. What the book talks about is this concept of direct stress. And this is how we set up the first portion of what we're looking at. And so our direct stress is we have some portion of a body, we have something, right? And we're either compressing it or we're pulling on it. Okay, for the purposes of this chapter, that's what we're reducing our analysis of the forces to. Okay? And we determine it using this equation. Okay, so this should look fairly familiar to us. We've come across this before, right? I prefer that they use this to model the stress, because I think that using the F can cause you confusion in that you may think of this as a force. Oh, and I'm sorry, they use a lowercase f, don't they? But we'll defer to the lowercase f to be consistent with their terminology. But we'll keep in mind that our units here are in PSI, they may be in KSI, right? It kips per square inch. Okay, this will be in pounds, and this will be in inches squared. Okay, so dimensionally we're keeping everything consistent. And so if we're using this measurement, we're determining some load per some surface area. Okay? So that's how they look at the direct stress. So what are some ways that we would be interested in that we may model? Okay, so the 2 examples that they give you is we have some square wooden block, and it's supporting a steel member and our wooden block is in direct contact with the soil, okay? And our support is transmitting 6,400 pounds. And if we translate, instead of looking at it in plan, or sorry, at grade, if we look at it in plan, we have an 8-inch square wooden post, okay? So the first thing that we have to envision and make sure that we understand is what has to happen for us to have equilibrium. What does the soil need to be able to do?
Support 6,400 pounds.
The soil needs to be able to support a minimum of 6,400 pounds, right? So we need to have a resistance force of at least 6,400 pounds. Okay, so for the purposes of this example, we're not going to examine that because we don't know any of the properties of the soil, but we'll just assume we have that capacity, okay? Now we want to know, we have our load, right? We have 6,400 pounds bearing completely on this cross-sectional area. We can determine the area of our post, can't we? Okay, so then we can determine our direct stress. All right? Our direct stress will be 6,400 pounds divided by the quantity of 8 inches times 8 inches. Yeah, and as Terry says, we have 6,400 pounds divided by 64 square inches. So our direct stress is 100 pounds per square inch. Okay? Seem reasonable?
A lot better.
Make sense to everybody?
This is a lot more feasible.
Yeah, it's a little more direct, right? Because now we're talking about specific examples. We're no longer talking about generalities. Right? Yep. So yeah, I think that this will go. I think that we'll be able to start picking up some momentum. So,
Not sweating yet.
example 2, which they don't work out, but they show. So we have some sort of steel cable. Okay, it's got a hook on an end, so it's going to support some weight. We don't know anything about it, but we know that our diameter is 1/2 inch. Okay? Oh no, I'm sorry, we do know. It needs to support a 1,500 pound weight. Okay? So again, first we need to make sure what has to be the case for equilibrium to be present. What do we need to verify at the interface of our cable and our, whatever this is, some sort of roof truss system, a ceiling, perhaps we're suspending from the bottom of a bridge, maybe we're talking about a sign, something of that nature. What has to be the case?
1,500.
We have to be able to hold in that 1,500 pounds. Now, the real world scenario, what's that?
So right there, we need, that base up there would need to be able to support it.
The cable, the hook.
Oh, the hook, yeah. So right there is where that we need to be
The interaction of our cable with whatever structure it's screwed into,
Picture
right?
the ceiling it's coming out of.
Yeah.
Yep. And this gets back to Kyle had asked last week when we were talking about, when we were doing those simply supported beams, we were neglecting the weight of the beam themselves, and Kyle had asked, when do we need to take this into account? In the real world scenario, right, it's not just the 1,500 pounds, it's the 1,500 pounds plus the weight of the hook, right?
Right.
But for the sake of this example, we're going to neglect the weight of the hook, okay? So, we set our problem up the same, where our stress is going to equal our force divided by our cross-sectional area, okay? We're assuming that this is a cylindrical cable, okay? So we have a circular cross-sectional area, okay? I won't give you any problems where you're gonna have to try and guess and figure out what kind of cross-sectional area you'll have. You'll be told whether it's square, whether it's circular, things of that nature, okay? So we need a little bit more manipulation here, but we have 1,500 pounds. And here we need the area of a circle, right? Everybody remember the equation for area of a circle? Pi r squared.
Circumference. 2 pi r.
2 pi r is going to give you the circumference of it. It's going to give you the measurement around. Yeah, the perimeter, exactly. Thank you. I wasn't coming up with that word either.
Wait,
But we're interested in,
He's doing it divided by 2 so he can get the half.
we're interested in this
oh,
dimension,
I thought that at first.
Okay.
not this dimension. Okay?
Okay, yeah.
I want to know if, because remember, we want to bear on that entire surface. We don't want to just bear on the perimeter of it.
because it's,
Yep.
the diameter is 0.5, you need the radius. So it's the same as pi.
It's the same as doing it
0.25.
before you put it on the paper. Yeah.
Right, diameter equals 2r, so our r will equal d over 2. Fair?
Mhm.
Okay. And so what does that end up being? Oh, I forgot to calculate this out. So that's 0.25, or I'm sorry, that's that's
Yeah,
0.25. So that becomes 0.625 pi, right? Roughly?
0.062.
What's that?
0.0625.
0.0, yes, thank you.
Quarter of a quarter.
Yep. Thank you. And so 5% of pi is what? 0.2? So, something like that? Is that what you guys are getting?
Thank you. Damn it.
Right? It's maybe 0.19 something?
Where the hell is pi?
Yeah, it's
0.19? Yep.
I know, can't find buttons.
So we have 1,500 pounds
3.14.
divided by, Logan, what did you say you got?
It was 0.196. So
0.196, okay? Okay, so that works out to be 7,640 PSI. Okay? I want to, before we go any further, let's stop and let's turn to page 49 in the text. 49 gives you a lot of common values. These are things that our manufacturers are doing testing all the time on their material for the wood and the metals. Okay? For concrete, we can design and do whatever we want and just use a conservative value, okay, for that determination.
He made it.
The second item down, I don't want to get into yield strength and allowable tension, Marshall.
Never mind, I answered my own question.
You got it? Okay. I don't want to get into the difference between yield strength and allowable tension yet, but look at what the allowable tension is for steel. 30,000 pounds, okay? So we're less than 30,000 pounds. So we are good, okay? Yes, sir.
How do you know if you're gonna use PSI or KSI? Will the question like state it?
Could give you, on that.
It'll be stated.
Okay.
The other thing to keep in mind is KSI, this is a very good question. PSI is pounds
And it's kilograms.
per square inch squared. KSI is what's known as kips per inch squared, and 1 kip equals 1,000 pounds.
Oh.
Oh,
So you can use them interchangeably. You could also say 7.64 KSI,
Okay.
and you're making an equivalent statement. You could also say 30 KSI, allowable stress for steel. Okay?
Who uses that? Is that just like a measurement used in forest only, kips?
Kips are only, yeah, they would only be used in forces and in load pounds.
Okay.
Yep.
That's never-
Yep.
Looking at massive units you don't wanna keep track of?
Yeah, yeah. So when you think about talking about steel and we're talking about a massive building, now we're gonna be talking about massive load. So talking in, it's just easier to say 30 kips than 30,000 pounds. Just allows us to talk faster, right? Is all that it does for us. So make sure to bookmark that table 2.1. You'll need that for the homework. Okay, and if any questions come up on the test pertaining directly to this that reference that, you'll obviously be able to use that as well. Okay? Is everybody good with this problem to this point? Before we move on, I want us to consider two other cases. One of the things that once we get into actually looking at steel and looking at concrete and looking at wood on their own is we're going to look at, as we size these things differently, what does that do for us? So what happens if we change the size of this cable? What's going to happen to us? What if we use a 1-inch cable? Is this going to help us? Is this going to hurt us?
In theory, it'd help.
It should help, right? So let's take a look at it. Well, let's change our diameter to 1.0 inch. What does that mean? Okay.
Well, wouldn't it still depend on the strength of what you're attaching it to? Though? Or we're not taking that into account for, I guess, so it doesn't matter.
We're not changing our load.
No, I'm not talking about that. I'm talking about like what the,
How you attach the cable to
to whatever the
Oh, I see what you're saying. Yes.
But we're not taking that into
Yep.
account, right?
Yep.
Okay, never mind.
Yes. Marshall's question is, if we increase the size of this, we're going to increase the weight of this. So we'd need to increase that resistance. And that's a very good point. Yes, in the real world, as we make these changes, it's not sufficient to just make this analysis. We also have to make this analysis. Very good point. Yep. But yeah, for now, we'll neglect the weight of the member itself. Okay, so we're not changing the load that we have to support. Okay, we're still supporting 1,500 pounds. But we are changing the diameter of the cable itself. Okay, or rod, or whatever it actually is in this case. Okay, so now we have, let's see, 1/2 times 1/2, so 0.25 pi, right?
Yeah.
0.79.
So 0.79,
Yeah.
okay? So now we have, what does that work out to be?
So they-
1910 PSI,
no.
okay? Roughly speaking, I just
Yeah,
rounded out to,
1898.
yeah,
Okay, yeah. Cool.
fair enough. In the grand scheme of things, in that we have an allowable stress of 30,000 PSI, does my cable care all that much about 1898 versus 1910, right?
Yeah.
And then from the perspective, now we have to think about, okay, what if this is supporting a running track? Okay? What's the economy for our owner in putting in 1-inch cable versus 1/2-inch cable? We're buying a lot more material, right? So we're making a more expensive structure. Have we improved
Yes.
our structure though?
Yeah. More difficult.
Kind of.
Well, isn't that a significant change in pressure versus?
It is. But are we worried about our material failing?
No.
Right? So let's look at what happens if we, okay. If you guys put in 1-inch cable, you're costing me too much money. I don't know. I've still got a lot of room. Can you put in a 1/4-inch cable?
That's fine.
Okay? So it becomes 1,500, what's 1/64th?
Well,
What does it become? didn't put that down either. What's that?
0.015.
0.015? Okay, so now we kind of blow up, right?
0.05.
30,560 PSI. If we move to a 1/4 inch cable. Do we want to be in that realm?
No.
The building code will freak out if we put in a 1/4 inch cable, okay? The building code doesn't want us to exert stress on steel cables greater than 30,000 PSI, okay? So yeah, so we could step, now we know, right? We ideally want to be somewhere between here and here, the 1/2 inch. If we can get a decent enough rate on it, that's maybe the way that we go.
It's crazy there's that much of a difference.
Well, it's all
right there.
It's
yeah.
all right here, right?
Mhm.
Because we're squaring that diameter, and then that's in the denominator. So yeah, as it gets smaller, it's starting to blow up our number. Yep. Okay. So does this make sense? If I give you questions like these, you'd be able to tackle them without too much difficulty, you think?
What do you think, Benny?
Yeah, so, yeah, we might be getting into it, so like the C,
Well, it looks pretty easy.
the cross sectional.
Yep, that's what we'll look at next. That's what we'll look at next. So, yeah, what Rush was asking is, so far we've just looked at F equals P over A, right? But just as with anything else, we can manipulate this equation to solve for whichever of these factors we want, right? We can use this to say, okay, I know the allowable stress of my material. I know the size of the material that has been specified by the designer. Now I can figure out how much load I can actually put on this thing. Or I can say, I know my allowable stress that the code will let me do. I know how much weight I'm putting on this thing. How big does it need to be? Okay, so this is how we determine how we're going to design and construct out in the field. Okay, so we'll look at example 3. It's actually, I guess, actually from your book, it's example 1 is what they call it, but so we're going to design a square post, okay? And we need to be able to have it carry 30,000 pounds. What size should this post be? Okay, so what are we trying to determine?
Area.
We want to know the cross-sectional area of this post, okay? So we'll start F equals P over A. If we divide both sides by F and multiply both sides by F, or sorry, multiply both sides by A, this will translate into P over F.
Yes.
Everyone agree? Okay? So we know that we need to have 30,000 pounds. Okay, if you turn to the table on page 49, tells you that for a structural wood member in compression, which is what we'll have, okay, parallel to the grain, so that's what we'll have to make sure that we dictate to our manufacturer. We need these posts manufactured so that this cross-sectional area is parallel to the grain. We're allowed 1150 PSI. Okay?
You always use 1150 when you're talking about the
When we're talking about
structural lumber.
Yep, when we're talking about structural lumber in compression,
Yep.
we'll always use 1150. Now, Terry brings up a good point. Does that mean that all the structural lumber, as soon as you put 1151 PSI on it, that it's going to completely disintegrate? Not necessarily. That's just the minimum allowable. Okay, so we designed to be conservative. What you'll probably actually see is you're probably looking at ranges from 1500 to 3000 PSI. Okay, and so we reduce that number to make sure that we have safe construction. Okay, and once we get through analyzing this, then we'll move on to the stress strain curve and we'll talk about those types of things and why we do that. Okay, so 30,000 divided by 1150 turns out to be 26.1 square inches.
So is that where you can leave the answer there? You don't want it to take the root of that so you get the dimensions, or assuming that it's a square post?
Assuming it's a square post.
So you can just leave it in the square?
Yep. Unless the question asks you to recommend, as this example does. This example wants you to take it further and say, okay, what size post should we actually build? Should we take this to a manufacturer and say, hey, make us a post 26.1 square inches? What's the manufacturer going to say to you? Hey, I'll absolutely make this for you.
But it's gonna be custom, I'm saying custom.
It's custom,
Yeah.
right, at this point?
5.7, right?
Okay? So if you flip to Appendix A8, that'll give you a lot of common, and what page is A8 on? Sorry, I forgot to mark it. Page 659 and page 660. Okay? And actually, we're just living on page 660. They don't have any of the square members. But you see our first member, so 3 items down, we have our 4x4. Okay? What do we need to remember about lumber? Is that our actual dimension?
No.
Now we're talking about a nominal dimension, right? But if we're dealing with a 4x4 square post, even if it is truly 4 inches square, is that sufficient area? It's not going to be sufficient, right? What about our 5-inch? We're still going to be shy, right? What about our 6-inch?
There you go.
6-inch, now we're talking, right? What's our actual cross-sectional area for our 6-inch post?
5.5, 5.5.
Okay, 30.25 square inches, right? So, what does that tell us about this particular support? It has more capacity than it's going to need, right? But that's okay. Wouldn't we be willing to over-design in this case and save on the economy rather than paying for the custom 26.1 square inch member? Okay? Does that make sense to everybody? What we're trying to do here? We need to figure out the minimum, and then we go and figure out what is available to us, and as long as it exceeds that area, it's sufficient to use. Okay? Next, let's look at okay, so we're looking at determining how much load a footing can carry. Okay? And our footing is going to be 2 feet square. When we flip over to page, what page did I say it was on? 49 or 59? I forget.
49.
Page 49? Page 49, our allowable stress for concrete is how much?
900.
900 psi. Now, for those of you familiar with concrete, does that seem like a low number for concrete?
Yeah.
It should, right? The reason being, we want to make sure that we have sufficient capacity with our concrete. What happens if we start getting close to this stress in our concrete? What's our concrete going to start doing? It's going to start cracking, right? And as soon as our concrete starts cracking, now we're going to open ourselves up to a world of problems. Okay, we're going to get things like chloride ion migration. We're going to get things like freeze-thaw durability issues. We're going to get into things like possibly coming out and having to epoxy things. We're going to get into issues like maybe we have to come out and core this thing at some point. Okay, so all sorts of things where we're going to have to get a third party out and investigate this system and see what's going on. Okay, so we don't want to allow ourselves to get too close to this. So, we know our stress, we know our area, so what do we need to do to manipulate our equation to figure out what's going on?
Multiply by area.
What's that?
Multiply by area.
We need to multiply our stress by our area to tell us what our load is that we can put onto this footing. Okay? Okay, but here's the problem. Dimensional analysis. Okay? Here we're in square feet, but here we're in square inches. So what do we have to do to modify this? We have to convert it to square inches. Please make sure that you use this and do not use this. Right? What happens if you multiply 4 by 12?
48.
Are you talking about, do you have 4 square feet? Okay. Make sure that you multiply it by 144. Okay? So we end up with 900 psi times 576 inches squared, which gives us a load of 518,400 pounds. Okay? So fairly robust, right? Make sense? Seeing mostly nods. Terry, good?
Yep.
Okay. One last example, and we'll look at, with this one too, we're going back to steel, so we'll talk about sizing the member as well. Okay, so here we're going to go back to our steel rod. Okay, for the ease of analysis, we're working out at a school and they want to add a running track. They don't have the space on their campus to have a running track. However, they have sufficient size in their gym to elevate it. And they have a multi-story school, so they're going to be able to access it from another floor. Okay, so structural engineers come in. He's done analysis on the roof trusses. It can take the overall weight of this track. So we need to figure out. The engineers come to us and said, "Hey, if you put in 7/8 inch rods, you're going to be good to go." Talk to the manufacturer, they're fine with building up the ends so that when they cut off those rods, you have that 7/8 inch effective diameter, okay, to build up that load. So we want to make sure, once people start using this track, that it's not going to completely fall down onto the gym class below. That would make us look bad, right? So we need each rod requires the ability to support 11,200 pounds, okay? So 5.5 tons. Rods are 7/8 inch in diameter. And, sorry, we should say in effective diameter, okay? So we don't have to reduce them based on shearing or any sort of end cutting that goes on with them, okay? So what is it that we need to determine?
That the 7/8 rods are,
Carry that load.
that they can carry 1,100 pound load.
200 pounds.
Yeah.
Is that what we want to determine?
No, you need to make sure that,
It's less than the stress
yeah,
It's less than what stress?
30,000
of steel.
pounds.
The allowable stress of steel
Oh,
of 30,000 pounds, okay?
But, so basically it has to be above the 1,100 pounds, but below the 30.
No, just below
Right.
30.
Careful, careful. Our allowable stress for steel is 30,000 PSI, pounds per square inch,
Oh, okay.
okay? This is telling us that these rods need to each carry 11,200 pounds. So that's the load that's being exerted on them, okay? We can use the load and their diameter to determine the stress on them.
So, oh yeah, so.
And then we just need to determine, is this less than 30,000 PSI?
Okay, so it's
Okay.
like over
So you gotta go
11.
11 to over 30,000.
Does that make sense to everybody? Jay, you're good?
So would it be
Yeah.
11,200
Kind of.
over?
Yeah.
So would it be 11,200
So
over
it's-
pi over?
0.6.
Radius.
0.6 is the actual amount.
So 0.6, it's 7 divided by 8 divided by 2 squared times pi.
0.8 something.
I got 18,666.
Right? 7/8 is 0.875. Okay?
Yeah, 0.6.
So what does that become?
0.6.
0.16?
0.6.
0.6? 0.6 pi?
No. 0.4.
That whole term.
Yeah, that's the other one. That's the other one.
That's what I'm saying,
And it's 18
Let me write this.
I got 18,666. Yeah, because 0.6, I just went from 0.6, I didn't.
Yep, I gotcha.
Anything, so 11,200 divided by 0.6. Well within the range of 30,000.
Okay?
So 18,600.
Good? I don't like 7/8 of an inch. That's too much material. Can we do half of an inch? What happens? Oops, sorry. 11,200 pounds, right?
No,
That'd be, you got 11,200 divided
So it's what? 11,200 pounds,
by. Yeah.
0.20.
what's that?
0.196, so round up to 0.
Oh, yes. Okay. So that gives us 56,000
no.
PSI? Can't do it, okay? Half inch is not a good idea. Okay?
So,
It's gonna lead to a lot of frowny faces, okay? Especially frowny face lawyers, which we always want to avoid frowny face lawyers, right? Okay, so do these types of questions seem reasonable, seem achievable for you from a homework standpoint, from a test question standpoint? Okay.
I have a question kind of off topic, but how do they calculate load when there's occupancy? Like a fluctuating occupancy. So like what do you do, because like not every person weighs the same, so that's a variable.
Sure.
So how do they is there like a mean they use, or like an average?
Yeah. Essentially what you'll do, and then you'll also use, so chapter 2 talks about factor of safety.
Okay.
And from a building code standpoint, you're not supposed to use factor of safety anymore. I'll tell you what actually happens is factor of safety gets used all the time. Okay, so, yeah, they'll use, assume the average American weighs 150 pounds. I don't know what the actual number is, okay? And your occupancy is going to be 300 people, okay? 300 people times 150, and then you'll typically multiply it by, structural engineers I think are usually using 2.5 or 3 as a factor of safety for live loads currently. So you'll plug that in.
Okay.
So, yeah, very good question. Factor of safety is used all the time. This is all in exact sciences, right? I mean, this all works out really nicely and it's very pretty with these examples, right?
Right.
When we use very nice, easy numbers. How the actual world works is, as Marshall brings up, how do you deal with live loads? How do you deal with the fact that in a theater, sometimes you'll have 10 people go to a movie, but sometimes you'll have 100 people go to a movie, okay? You'll design for 100 people all the time, okay? Saying that that's the maximum occupancy.
Max.
Yep, yep. And then as long as you can safely operate at maximum capacity, everything else is just less economy for the owner, such as it is. Okay.
My question was, it looks like on C, that we need to figure out the cross-sectional area. Is that just talking about, are we solving for the diameter?
What page is this on?
It's on 51,
Is it like a
2.1.C.
Steel bar.
So it's.
Okay, so problem 2.1 point C, determine the minimum cross-sectional area of a steel bar required to support a tensile force of 50 kips if the allowable unit tensile stress is 20 KSI. Yeah, so that's this problem here, right?
So we're just, well, isn't it asking us for, would it be more like that problem with the diameter and the pi and all that? Because
It's not wrong.
it's asking us for a cross-section of a bar. So it's,
And that's area, right?
Area.
okay, so I was just reading it confused.
Yep. No, it's fine. And so, Rush, what I would think of again is when you solve this, you're getting some area.
Yeah,
That's the minimum cross-sectional area that you're going to need. Okay? Steel and timber are different than concrete, right? Concrete, we can go out on site, build up our own forms and set them into place, order ready-mix trucks and say, hey, look, I've made this fantastic place for you, you can place all your concrete here. Okay? Steel and timber, we go to the manufacturer and say, hey, what types of things are you commonly making that I can get that are at least this size? Otherwise, as Marshall said, we're getting into custom work. Okay? And there are times where we may not be able to get away from custom work. Okay? All we have to do is make sure that we communicate that to the owner. So does that answer your question, Rush?
yeah, I
Kind
think
of.
the biggest thing that, like I was getting hung up with, because one's the kips and one's KSI, so I was like, well, how does that?
So keep in mind, kips is
Yeah, that's what I
1,000
was-
pounds, and KSI is kips per square inch.
So it'd be KSI per kips. That's what's driving me nuts, is like the label for it. So I'm getting for that problem in particular, it'd be 0.4 KSI per kips.
It's also pounds per square foot on that problem, Rush, not PSI.
KSI.
KSI.
It's 50 kips, the unit tensile strength of 20 KSI.
Mm-hmm.
Yeah.
So when you work out the equation, you just divide 20 divided by 50, it's 0.4. It's pretty simple, but 0.4 KSI per kips, that's what I'm getting at.
Oh, okay, I got you.
Or do we convert that into like some other,
So let's back this
just
off
asking for an
then.
area, you know where I'm
So if
getting
I
it up
give you
here?
pounds and PSI, and I want an area, what are you gonna do?
It'd be PSI.
Oh, you gotta convert it.
No,
into
I want
square
area.
inches.
What's your unit for area?
Square inches.
Okay. So how are you gonna convert these two data points into square inches?
Divide,
You're gonna divide what?
PSI by pound.
Careful.
Pounds?
Do you wanna divide PSI by pounds?
Or pounds by PSI.
Pounds by PSI, yep. So if we do pounds, because PSI, all we're saying is pounds per square inch, correct? Okay, our pounds will cancel. And then we're left with 1 over inches squared. And isn't that the same as inches squared?
So using that, kips and the KSI, obviously the kilo or the K would cancel out. And it's then pounds per square inch and,
Yeah, so there's two ways you can go about it. You could write it as kips over kips per square inch. And that should get us to here, right? Because these are the same unit, aren't they?
yeah, but it's kips and KSI. It's kips over KSI.
Right, but KSI is just kips per square inch,
Okay,
right?
Kids-
so it's just square.
It's like pounds over PSI.
I'm just trying to figure out the process here. I don't understand.
Are you gonna upload this too, just in case if we need like a refresher?
Upload what?
The video on Canvas?
Yeah, this'll go up, not on Canvas. I don't have enough room to put this on Canvas. I'll keep putting it up on that YouTube channel.
Oh, the YouTube channel. Okay.
Got,
I got it.
Is that linked on Canvas though? The YouTube channel?
I believe so. I'll make sure if it isn't, yeah, that it will be. I think that I put it in discussions. I'll check to make sure that it's there. Good? Okay.
I was just getting hung up on that title.
Yep. Yeah, I agree with you. Yeah, this KIPS, I imagine, is something that all of you may not be familiar with. Okay? So. Let's see, let's get rid of this. Okay, so after we get done with direct forces,
2.5.
Huh?
It's just 2.5.
0.4.
we talk about deformations.
20 divided by 50.
What is a deformation? Remember from the terminology?
Something that causes, shape, size,
Yeah.
changes,
What causes it?
stress,
Careful. It's a force.
force.
Force, right? Remember that our force is different than our stress. A stress is when we're working over an area, okay? So, anybody, two words, right? Not anybody. Any body that has a force exerted on it will have a change in shape. Okay? This chapter deals only with axial forces. Okay, so the deformations that we're going to deal with are linear deformations. What does that mean? As we compress a concrete cylinder, what is happening to it when we're thinking about deformations? In this dimension, is it getting longer or shorter?
Shorter.
It's going to get shorter, right? We're compressing it. If it's getting shorter in this dimension, what's happening to it in this dimension? It has to get bigger, right? We cannot create or destroy matter, okay? We have a certain amount of concrete, so it can't be destroyed. It has to change its shape. Okay, so they talk about deformations. The big takeaway, let's see. Oh yeah, we should talk about, there's essentially, well, two thresholds that we would have, but we'd have three different cases. If I were to take this concrete and push on it with my hands, can we see the deformations that are happening?
No.
I'm not strong enough, right? If I put this in the compression machine and let the compression machine run, could we start seeing the deformations that occur? Absolutely, especially once we fail the thing, right? We'll definitely be able to see the deformations. In between, there are areas where we have deformations that we're fine with. We're okay with picking up a little bit of distance, right? That's why we put things like expansion joints into materials. That's why we allow those spaces between those interfaces so that things they can spread out, they can contract as needed. Okay? Another thing, maybe all of you are like me, I try to avoid the Mall of America as much as I possibly can. But there are times in my life where I have to go there. Okay? For instance, when it's school break and the kids want to go to the Crayola experience. But when you're there around the holidays and it's packed with people, and you're walking over the suspended areas between, have you ever noticed anything as you're walking?
Flex.
Do you get a little bit of vertigo as it's flexing, right? Okay, so we have to be mindful that if we have too much of those deflections, think about if we have too much deflection in the joists of a house, what could we potentially impact? The joists themselves might be fine.
Ceiling material?
Yeah, we may start cracking joints in the sheetrock. Okay, we may, if we have larger deflections in larger buildings, we may have issues with mortar joints. We may have issues with doorways. Okay, so we have to see and make sure that we're aware of what's going on with our
Bridges
deformations.
are like suspended, like stuff like that's engineered to flex though, right?
Yep.
And have buoyancy to it.
Yep.
So it doesn't
Exactly.
stress fracture
Yep. Yep.
or have
Yep.
a major failure.
Yep. Exactly right. Exactly right. So, we're introduced to the concept of strain, where strain is your change in length over your initial length. And so, when we're thinking about these deformations and what we're defining as what's allowable, do you think, off the top of your head, is strain going to be a large number, or is it going to typically be a small number?
Hopefully small.
That's a good point. That's a good point. Kurt said hopefully small, right? Hopefully our strain is small. What happens if our strain is big?
It's gonna fail.
We could definitely end up with failure, right? In fact, if we have strain greater than 1, what does that tell us?
That's not a
We've increased that length by 100%. Okay, so it could be very, very bad depending on what our material is. All right? So we will oftentimes deal with what's called the stress strain curve. Oops, sorry, pushed myself a little too far out to the edge. Okay, so our strain will be on this edge. So this is in your book, I forget what page.
53.
53, thank you, Jay. We have a handful of points that we're interested in. We're very much interested in this portion of the curve. What do you notice about this portion of the curve? Specifically pursuant to the slope of that curve.
Steep.
It's steep. Does it change? I mean, it does because I'm pretty poor at freehand drawing a straight line, right? But assuming I had a ruler, right? This is a straight line. That's called the elastic area, okay? We like our materials to be in an elastic area. The reason being, if I compress on this concrete, but the compression that I do is in that elastic limit. When I take the load off, it goes right back to its initial shape. We like that in our constructed world, right? We like things to stay, generally speaking, in the shape that we make them in. So the first point of concern for us is the yield strength. When we're talking about steel and when we're talking about wood, the allowable stress, let's see, equals our yield strength. Okay? Once we get to the yield strength and we keep loading that thing, whether it be steel, whether it be wood, whether it be concrete, plastic, it doesn't matter what it is, it will not go back to its original shape. It will undergo some strain hardening. Okay? And so what that means is it starts to permanently deform. What happens in steel is a concept called necking, where you'll see a portion of the steel itself will change shape and actually thin out. Okay? What is happening right here?
It's getting stretched.
It's getting stretched and it's becoming more brittle. Okay? Brittle material is more prone to sudden failure. And we want to avoid sudden failure at all costs. Sudden failure does not give us time to get people out of the building, okay? Or off a bridge deck, or underneath a suspended running bridge, or anything of that nature, okay? So we don't like being in this area, okay? We also don't like being in this area, ultimate strength. Ultimate strength means once you get here, there is no coming back. We no longer have one piece of steel or one piece of wood or one piece of concrete. We now have two pieces. Okay? This is where people certainly die. Okay? What happens is once we get past our yield strength, now it's just a number of cycles as we continue hardening the steel until we get to our ultimate strength. Okay? So, I'm not going to ask you to generate this curve. I'm not going to ask you to run a lab where we're doing things, but just be aware of what these two concepts are, specifically with respect to the stress and strain curve. Okay? What does ultimate strength mean for a material? What does our yield strength mean for our material? Okay? Within our elastic area, though, we can determine a material's stiffness. Okay, so how much does it resist bending? And that's modulus elasticity is somewhat important to us for timber, less so than it is for steel and concrete. As steel and concrete, we're typically building much more massive structures. So we need to know what that stiffness is. How much is this? How much are these members going to flex as we're loading them? Okay. So our modulus elasticity, generally speaking, you can think of it as your stiffness of material, and it is, let's see, it is your stress, which I'll continue using F, because that's what your book uses, divided by your strain. Okay? But what do we know that F is equal to? It's equal to our force divided by our area. And what do we know about our strain?
It's the change in length over the original.
It's our change in length divided by our original length. So we could also say that our modulus elasticity is equal to, nope, that's not correct. Our loading condition times our initial length divided by our area multiplied